Thanks for the introduction. Hello, and welcome to my presentation about COCONUT-SVSM. I'm going to talk about the current state and the future of the project. So, but first, some introduction to the project. So the first big thing you see here is our brand new project logo that we got a few months ago, thanks to Diona Claes from Google, who initiated and drove this effort. So many thanks for that. The project has a logo now. So, but now into the topic. So what is COCONUT-SVSM about? COCONUT-SVSM, in a nutshell, is a platform to provide secure services to confidential virtual machines. So how does COCONUT-SVSM achieve that? First of all, it runs in CVM context. So it's a piece of software that runs within the encrypted and protected context of the confidential virtual machine itself and is protected by all the guarantees that the trusted execution environment gives to software running within it. While running in the confidential VM, it is still isolated from the guest OS. So the guest operating system has no way of accessing any memory of COCONUT-SVSM, which is an important property because it allows to actually hide secrets and state from the guest operating system, which is needed for providing secure services. The project is written in Rust, which should avoid some of the common security problems. And with all of that, it makes it a platform for providing secure services. So what services are we actually talking about that COCONUT-SVSM can provide? These are services that are without confidential computing, are usually provided by the host hypervisor, but which can no longer be provided by the host hypervisor in a secure way, because the host hypervisor is not trusted anymore. The most prominent example is, of course, the Virtual Trusted Platform Module, the VTPM. This is a service provided by the host VM that cannot in any form securely be provided to a CVM by the host hypervisor. So, but it can be provided by COCONUT-SVSM in a secure way to the guest. But there are other use cases. One is live migration that can be provided in a secure way, or can be achieved with the help of the SVSM for a confidential virtual machine. Then another possible use case is a UEFI variable store, which would enable a secure boot in CVMs on some platforms. Or even on some platforms, it could even provide a secure interrupt controller when the hardware does not provide it. The project is on GitHub, so it was actually published 2 years ago. Actually quite here at OC3, so 2 years ago it went public and it attracted quite some community since then, which I'm very thankful for. So from here, a thank to the community for all the great work. But now I want to dive a little bit into the security architecture. What are the design decisions that make COCONUT-SVSM a secure choice for providing these secure services? The most important and fundamental decision, and one that was made very early in the design process, was to write COCONUT-SVSM in a way that services can be provided by code running in CPL3 or in user mode, which gives the code that provides the actual services the least privileges. So there's actually no good reason why the services that COCONUT provides should not run or need any of the privileges that, for example, an operating system kernel has. And this choice also allows the services to be isolated from each other, because when you have a problem in one service, it is unlikely to escalate to another service. So this was one design decision of COCONUT-SVSM. And the other design decision is something I call address space minimization, which is an implementation choice of the COCONUT-SVSM kernel, which is not so common in standard operating systems, but it makes sense for a secure platform. So the goal is to have execution contexts with minimal private mappings. which means that there's a task concept in the COCONUT kernel, of course, that is needed for user mode as well. But everything that is owned by the task, like the per task stacks, is only mapped in the task context. Other tasks cannot access the stack of the currently running task. Same with per task private memory, that is also private to the task itself and cannot be accessed by any other tasks. And what is true for tasks is also true for the per CPU memory of the COCONUT kernel. This is also only mapped on the current CPU and not accessible by any other CPU. And with this address space minimization, every execution context only has the memory map that it actually needs, which lowers the ability to exploit any bug. So this was the security architecture of COCONUT-SVSM. Now I want to dive a little bit into the advancements the project made over the past 2 years. So the community actually achieved quite a few things. One is, of course, the virtual TPM service. That is the initial main use case of the SVSM. So this is currently available in the code base. You can compile the SVSM and get a VTPM in the virtual machine. There is a Linux driver currently under review. So this can be used. The TPM is still ephemeral, so each time you boot, there is a new root key generated, so you cannot use it to store a disk key, for example, because there's no persistence yet. More on that later. Hypervisor support is something we extended quite good on, because initially the project was developed on the KVM QEMU platform. This was extended, meanwhile, to also support Hyper-V. And the COCONUT-SVSM also runs on the Google Cloud hypervisor called Vanadium. We switched to IGVM as the standard packaging format. So IGVM is basically a format that can describe the initial memory layout or the initial state of a confidential VM, which has some nice benefits because there's tooling which takes an IGVM file and calculates the expected launch measurement of your virtual machine. And when you actually boot from that IGVM file, you can compare the actual launch measurement to your pre-calculated one, and this way you have the proof that the hypervisor loaded your file correctly and your initial memory layout was as expected. And the SVSM makes a lot of use of that because IGVM is the only method it can be deployed today. Platform support, we also extended quite a bit on that. So initially, it was developed for the AMD SCV SNP platform, but support is evolving for Intel TDX as well to support TDX partitioning environments. And we also support the virtual secure mode for Hyper-V, which is a software-protected environment. So this is now supported as well. And of course, user mode, I said this is a big selling point of the SVSM. This has come a long way. It's almost there. SVSM can execute user mode processes. A few pieces are still missing. More on that later. And also a great thing that happened recently is the introduction of formal verification for parts of the code base, not for the whole SVSM. That's not yet feasible, but some parts of the code can be formally verified. So this is, in a nutshell, the main things we achieved over the last 2 years. But of course, the project is far from being ready. So what are the future directions? What do we want to achieve? What is under development currently? So most prominently, we want to finish user mode. That's, of course, what I already mentioned. So to finish user mode, we still need some user mode support code, so we need a user mode support library, and we need to finish the syscall interface to allow user mode to actually interact with the guest OS. These are the two pieces that are not completely finished yet, but this will hopefully be ready soon. A persistence layer is also under development. So there is a PR pending from Red Hat for a VirtIO block device driver. This is hopefully going to be merged soon. Based on this VirtIO block driver, we also need an encryption and file system layer, which is also currently being discussed. So with that, we get persistence in the COCONUT-SVSM, and services can actually store persistent data, which can be restored after a reboot. So with this, you can we will get a persistent TPM, and you can actually start using the TPM to store, for example, your disk key, and unlock the disk of your CVM automatically at boot once all the attestation passes. Attestation is another thing that is currently under development. So the main goal of the attestation in the SVSM is to actually talk to a key server to obtain the secret for the persistence layer, to basically unlock the persistent data that the SVSM wants to access. There are two approaches here currently. Both use a proxy because the SVSM itself has no network stack, so it cannot talk to any remote key broker service. So there are, as I said, there are two ideas here. One is to have a proxy on the host side, on the host hypervisor, and let the SVSM talk to that. And the other is to have the proxy run within the guest OS environment. So currently, I think it's the UEFI environment where the proxy runs, because our VMF has a network stack, so this can talk to a key broker service, which is remote. So another thing that is currently ongoing is the SVSM bus. That is going to be a standard communication interface for service drivers within the guest OS to the SVSM, which is platform independent. So the idea is that the SVSM bus abstracts all the specific communication mechanisms for the different CVM technologies, like SEV and TDX and in the future ARM. And then have a common set of service drivers on top of that can actually talk to the SVSM services in a platform-independent way. So, for example, we can have a generic TPM driver that works on all platforms, or a generic observability driver to actually check what the SVSM is doing, or something else. Another thing which I'm pretty excited about is establishing Coconut as a Rust target, so that you can basically get support for the Rust standard library to write secure CVM services, which will open the possibility to basically include any crate from crates.io that requires a standard library. With the Rust target support, you can use all of them or any of them to basically write your services. And this is actually a prerequisite for the next thing we want to achieve in the future, and that is paravisor support. Having paravisor support will turn the SVSM, or will turn COCONUT-SVSM from a pure service module or from a pure service platform to a full in-guest paravisor, which can actually help run operating systems within the CVM that are not fully enlightened to run there, for example, Microsoft Windows. So this is something we are looking into and we are working towards. There's, of course, some road to go there. But actually, to achieve this, having Coconut as a Rust target is needed, because for that, we are currently looking into running the OpenHCL project, which is covered in a parallel talk, I think, porting that project to the Coconut platform and run it there and turn the COCONUT-SVSM into a paravisor this way. So this were the future plans for the project. And with that, I'm done with my talk, and thank you, everyone.